Welcome back to the deep dive. This is where we really try to cut through the noise around the latest AI and machine learning research.
Yeah, give you that clear picture of what actually matters.
Exactly. And today we're plunging into something that, honestly, it feels like it reshapes the very foundation of global AI. It's this huge challenge, right? Scaling these powerful multimodal models beyond just, well, beyond English.
It's a really crucial deep dive.
Yeah.
Because when you think about models like CLIP, Contrastive Language-Image Pretraining, I mean, their capabilities are just incredible. I mean, kind of the silent engine behind so much stuff we now just take for granted, helping LLMs see, powering smarter image search.
They've really shifted how we interact with information, both visual and text.
Totally transformed it.
But it's surprisingly easy to overlook just how narrow that powerful lens has been, hasn't it?
It really has.
These foundational models, yeah, they're strong, incredibly strong, but they've been overwhelmingly trained on English-only data. And when you actually look at the internet, the sheer scale of it, that's a massive blind spot.
It is.
Think about this statistic. A staggering 50.9%, basically half of the World Wide Web data is actually non-English.
That number really hits home, doesn't it? It's not just like an interesting factoid. It really underscores the core problem we're talking about.
Yeah.
If your foundational AI models are essentially missing half the world's available information, well, you're just not building truly global AI, are you?
You really aren't.
So the challenge becomes, okay, how do you expand these models? How do you get them to incorporate truly worldwide data without just hitting a wall?
Because it's not as simple as just throwing more languages at the problem, is it?
No, definitely not. There's this well-documented phenomenon, particularly in large language models, but we see it in multilingual vision models too. It's called the curse of multilinguality.
Ah, yes, the curse. And that means, if I'm getting this right, that actually adding more languages can make the model perform worse on the main language, like English in this case?
That's exactly it. You train it on more languages, and suddenly its performance on English tasks dips compared to an English-only model.
So we've been stuck in this kind of lose-lose situation. Either you have a great English model or you have a multilingual model that's maybe okay, but it sacrifices that peak English performance.
Precisely. It creates this dilemma. It made it seem like a single, unified, high-performing model for everyone was maybe, impossible.
A fundamental roadblock.
Yeah.
So today, our focus, our mission for this deep dive is to really unravel a groundbreaking new paper from Meta. It's called Meta CFIL 2, a worldwide scaling recipe.
And the claim is pretty bold.
It is. They claim to have not just, chipped away at this problem, but to have actually cracked the code.
Right.
We're going to explore the technical innovations here. How did Meta CFIL 2 manage to overcome these hurdles? And crucially, how did they make it so that worldwide data actually benefits the model overall?
Creating a single model that excels everywhere. English, non-English contexts.
That's the goal. And we're going to focus squarely on the technical breakthroughs, the nuts and bolts, and what they mean for how these models are built and how they perform from now on.
Sounds good. Let's get into it.
Okay, so let's peel back these layers. To really appreciate what Meta's CLIP 2 achieves, we first need to get a solid handle on the CLIP itself, the fundamentals, and the roadblocks that stopped it going global before now.
Makes sense.
So maybe at a high level, how would you describe CLIP's core function? For someone who follows AI, maybe knows the basics, but isn't necessarily training models day to day?
Sure. Okay, so at its heart, CLIP, Contrastive Language-Image Pretraining. It's all about teaching AI to understand the connection, the relationship between pictures and words.
Like a sophisticated matching game.
Kind of, yeah. Imagine feeding it millions or even billions of image-text pairs from the internet. Like a photo of a golden retriever, and maybe the alt text says, a happy golden retriever running in a park. CLIP learns to create these versatile numerical representations, as we call them, embeddings, for both the image and the text. And the goal, the contrastive part, is to make sure the embedding for the picture of the dog ends up really close to the embedding for the text about the dog in this shared multi-dimensional space.
While being far away from embeddings of, say, cats or cars.
Exactly. It learns what matches and what doesn't.
And once it learns that alignment, that shared understanding, what does that actually unlock? What can it do?
Oh, the applications are pretty wide-ranging. One big one is zero-shot classification.
Right, the one you mentioned earlier.
Yeah, it means the model can identify objects or concepts it wasn't specifically trained on during that initial phase.
So it generalizes.
Precisely. You could show it a picture of a quokka, You know, that little Australian marsupial.
The happy-looking one.
That's the one. Even if it's never seen a quokka image before, if it understands the word quokka from text, it can often correctly classify the image. It's essentially learning to generalize from text descriptions.
That's powerful.
It really is. It's also crucial for image retrieval, finding images based on text queries, or the other way around. That's central to a lot of search engines now. And critically, especially in today's AI landscape, CLIP models serve as these vital vision encoders in multimodal large language models, MLLMs. They basically give these powerful language models eyes, letting them see and interpret visual information.
Okay, so it's clear why they're so foundational. But like you said earlier, they've been largely English only. What was the fundamental reason? Why haven't we seen truly global models until, well, now? Was it purely a technical hurdle?
That's a great question. And yeah, historically, the big foundational CLIP variants, OpenAI CLIP, the original Meta CLIP, they put huge effort into curating billion-scale data sets. But crucially, these were almost exclusively English.
Right.
The key issue really boils down to how these massive data sets were built. There are kind of two dominant approaches, curation from scratch and distillation from external resources. And understanding this distinction really highlights the barriers they faced.
Okay, let's break those down. What's the difference? And why did one make global scaling so much harder?
Okay, so curation from scratch. That's when you're building the data set directly from raw internet data, like web pages, maybe from Common Crawl or something similar.
Starting fresh.
Exactly. But the crucial part here is that researchers meticulously construct the data. They align it with human-defined concepts. They use high-quality, transparent sources, like WordNet synsets.
Synsets, those are like sets of synonyms representing one idea, right? Like cat and feline pointing to the same concept.
Precisely. They also use Wikipedia data, single words, unigrams, two-word phrases, bigagrams, page titles. It's very much a model-free and transparent approach.
So you know what's going into it.
You know exactly how your data is being built, which concepts are getting emphasized, what potential biases might be creeping in from your choices. It's a very controlled process.
Okay, controllable. And the alternative, distillation.
That sounds like where the problems for global expansion started. That's generally been the trickier path for global scale, yeah. Distillation from external resources involves training models on datasets like LAON or WebLI. These methods often rely on what are basically black box filtering processes.
Black box, how?
Well, they might use an existing, already trained CLIP model, like an OpenAI CLIP, as a teacher. It filters or scores the data, essentially saying, yeah, this image and text pair looks good to me, keep it.
Ah, okay.
Or they might use proprietary private data sources, like WebLI apparently uses Google image search results, but the inner workings of that aren't public knowledge.
Right, less transparency. And why is that a problem, specifically when we're talking about scaling globally and trying to minimize bias?
The big issue is that these distillation methods introduce what the Meta CLIP 2 paper calls untractable bias and less controllable data distributions.
Untractable bias, meaning you can't easily trace or fix it.
Pretty much. If the teacher model you used for filtering was English-centric to begin with, which it likely was, it's naturally going to propagate that bias. It'll subtly filter out or misrepresent non-English concepts, even if the original data was multilingual.
So the bias just gets baked in deeper.
Exactly. You don't really know why the teacher model preferred certain pairs over others. This lack of transparency and control makes it incredibly difficult to truly scale these models to worldwide data and ensure you're getting diverse, unbiased representations that genuinely reflect the global internet. You're essentially building on potentially shaky bias foundations.
Okay, that paints a clear picture of the historical landscape. So let's dive into the specifics then, these worldwide scaling challenges that Meta CLIP 2 aimed squarely at solving. What were the two really big fundamental hurdles they identified?
Okay, the first major hurdle was simply the lack of a fundamental, robust data curation method specifically designed for non-English data at scale.
It just didn't exist.
Not in a way that met the standards of the curation from scratch approach used for English. Historically, attempts to bring in non-English data, they often resorted to simpler, less precise methods.
Like what?
Well, for instance, some models used machine translation. They'd translate non-English captions into English, or maybe English descriptions out to other languages.
Well, translation isn't perfect, right?
Far from it. Machine translation can introduce its own biases. It often loses cultural nuance, or it just results in lower quality kind of synthetic data that doesn't really reflect how native speakers would naturally describe an image.
Okay, so translation was one flawed approach. What else?
Other approaches relied on that distillation method we just talked about. So they inherited biases from their English-centric teacher models, or they used private, non-transparent data sources. There just wasn't a transparent from-scratch method to process potentially billions of native, non-English image text pairs directly from the web in a controlled, conceptually grounded way.
So it wasn't just about finding the non-English data, which is already hard. It was about finding good data and having a principled way to process it, respecting its original meaning and context.
Exactly right. And the second challenge, the one we touched on earlier, is maybe even more counterintuitive, the curse of multilinguality.
Right, the performance drop.
Yeah, this phenomenon, where adding more languages during training can actually lead to worse performance on the dominant language, usually English, compared to a model trained only on English data.
It still feels weird that adding more information makes it worse at its original task.
It does seem counterintuitive. It's like trying to learn too many instruments at once, maybe. You end up just okay at all of them instead of mastering one.
Yeah.
That's kind of the effect here.
Can you give us a concrete example of this curse in action? Did the paper mention one?
I did, yeah. A clear illustration comes from comparing MSiglip, which is a multilingual CLIP variant, with its English-only counterpart, Siglip. They found that MSiglip is 1.5% worse than Siglip on ImageNet. And ImageNet is a standard benchmark, mostly for English vision tasks.
So the multilingual version actually performed worse on a core English test than the English-only version. That 1.5%, that's not nothing.
It's definitely not trivial in these large-scale models. It's a measurable step backward, confirming the curse was a real issue.
What were the practical implications of that for developers or researchers trying to use these models?
The immediate implication was inefficiency and fragmentation. If you needed the absolute best performance, you were basically forced to deploy separate models.
One for English, one for everything else?
Pretty much. One specifically tuned for English tasks and another one, probably the multilingual one, for other languages. This redundancy adds significant complexity, development, maintenance, deployment, and just makes everything harder.
And prevents having one single, unified, high-performing model that could serve everyone globally.
Exactly. It made that global ambition inherently costly, either in terms of performance trade-offs or just operational overhead.
So, for years, this curse, combined with the lack of good non-English data curation, they really hamstrung the global ambition for models like CLIP.
Severely limited it.
But MetaCLIP 2 claims they found a way, not just to mitigate these problems, but to actually turn them into mutual benefits. That's a really bold claim.
It absolutely is, and that's exactly what we need to dig into next. The specific technical innovations, the recipe that makes MetaCLIP 2's approach so different, so groundbreaking.
They engineered it, you said, to be a win-win.
That was the goal. No compromise, just synergy.
Okay, we've definitely set the stage. Now, let's really get into the weeds of the MetaCLIP 2 recipe. This paper feels like it's about more than just adding languages. It's like a fundamental shift in handling global data at scale.
I think that's fair to say.
What was the core philosophy driving MetaCLIP 2's development? What was their guiding principle?
Well, their core philosophy was really ambitious and quite rigorous. They set out explicitly to train CLIP from scratch on native worldwide image-text pairs.
From scratch. Native pairs. Worldwide. That sounds like the trifecta.
It really is. And crucially, this meant they avoided relying on outsourced resources, private data, machine translation, or that distillation technique we discussed.
A clean break from previous shortcuts.
Absolutely. A critical departure. Their aim was to build this robust, transparent foundation for global multimodal understanding. And they tried to maximize overlap with OpenAI CLIP's vanilla architecture, the basic setup to make sure their findings were as generalizable as possible.
So others could potentially build on it using similar models.
Exactly. No shortcuts, no black boxes, just raw worldwide data managed very, very carefully.
That sounds like a monumental task just in itself. So what was the first big innovation, the piece that actually laid the groundwork for this whole curation approach?
The first innovation, really the bedrock of their whole curation system, was building worldwide metadata.
Metadata, like data about the data.
Exactly. The problem, as we discussed, was that English CLIP models had access to this incredibly rich, human-curated metadata. Things like WordNet, Wikipedia concepts. Essential for defining concepts and structuring the training data in a meaningful way.
And that just didn't exist for other languages at the scale they needed.
Right. That level of quality, that conceptual richness, was simply missing for most non-English data, especially at the scale of billions of pairs.
So how did they solve that? How did they manage to scale that kind of quality and conceptual depth to hundreds of languages? That sounds almost impossible.
It was a massive undertaking. Their solution was essentially to replicate and scale this meticulous metadata curation process to cover over 300 languages. They tackled it in three main ways.
Okay, what were they?
First, they incorporated multilingual WordNet. This includes those synsets groups of words with the same meaning, pulling them in from 31 different languages where available.
So extending that conceptual backbone.
Precisely. Second, they processed huge amounts of Wikipedia data. They extracted unigrams, single words, and bigrams, two-word phrases, from Wikipedia dumps across an incredible 329 languages.
Wow, 329 languages from Wikipedia.
Yeah, and this presented its own technical challenge, especially for languages without space separation, common in many Asian languages where words aren't clearly divided by spaces.
How did they handle that? Just splitting randomly would destroy meaning.
Right. So they cleverly leveraged open-source tokenizers developed by local communities. These are tools specifically designed by people who understand those languages to accurately break down the text into meaningful words or units, preserving the semantic integrity.
Smart, using community tools. And the third piece of metadata.
The third piece was Wikipedia titles. They took page titles from 40 random dates and then ranked them by click-through traffic for each language separately. This helped them identify the most prevalent and culturally relevant concepts globally, language by language.
Okay, that's a truly massive, multi-pronged effort just to build the metadata. And I noticed they mentioned a key design choice: independent metadata per language. Why was that so important? Why not just mash everything into one giant multilingual concept list?
That's a really sharp observation, and it's crucial. The paper explicitly highlights why independent metadata per language is necessary. They give the example of the word mit.
MIT, M-I-T.
Yeah. In English, mit might be shorthand for mittens, but in German, mit means with, totally different concepts.
Ah, okay. Homographs across languages?
Exactly. If you just combined everything, the model would get confused by these identical-looking words with different meanings. By keeping the metadata language specific, they ensure the model learns concepts accurately within each distinct linguistic and cultural context.
Avoiding ambiguity.
Right. It gives much more granular control over the semantic space for each language, leading to better performance and avoiding that kind of confusion.
That makes perfect sense. Context is absolutely key. Okay, so now they have this massive, carefully curated, language-specific, worldwide metadata. How do they actually use it to process the billions of raw image-text pairs scraped from the web? That brings us to innovation two, the worldwide curation algorithm. How did they adapt the original meta-CLIP algorithm for this truly global scale?
Right. So just to quickly recap the original English meta-CLIP algorithm,
Right.
it used substring matching, basically checking if parts of the image caption matched entries in their English metadata.
Finding keywords.
Pretty much. It then counted these matches globally, entry count, and used that to balance the data.
Yeah.
This balancing involved setting a sampling probability based on a threshold.
The threshold.
Yeah, like 170,000 matches for the original meta-CLIP. This threshold was designed to ensure that tail concepts, ideas that are less frequent but still important, were sufficiently represented. It stopped the model just learning about the most common head concepts.
So, ensuring a balanced diet of information, not just the most popular stuff.
Yeah.
Got it. How did they adapt this balancing act for a multilingual world? Concept frequency must vary wildly between languages.
You've hit the absolute core challenge there. The first step in their worldwide adaptation is language identification, or LID. For every single image-text pair they pull from the web, the algorithm first has to accurately figure out the language of the alt text.
Okay, step one, know the language.
Crucial step, because that classification then directs the algorithm to use the correct language-specific metadata that they built so carefully.
Makes sense.
But here's the really clever bit, tackling the problem of that threshold T. Just applying one single global T to all 300-plus languages. Well, it's just suboptimal. Wouldn't work well. Because data sizes and the sheer number of concepts differ vastly across languages. If you applied the same T to a language that has much less available data online, you could end up severely diluting its tail concepts. You'd overemphasize the common stuff and lose the nuance from the less frequent but potentially unique concepts in that language.
Right, because what's common in English might be rare in Swahili, or vice versa, just based on the data they could find or cultural focus. A universal T would just flatten all that important diversity.
Precisely. So their really ingenious solution was to derive a unique twang, a language-dependent threshold for each and every language.
Okay, how on earth did they calculate a specific T for hundreds of languages? That sounds complicated.
It sounds complicated, but the principle they used is quite elegant. They leveraged an invariance assumption that came out of the original meta-SIL-OP design. The assumption is that you want to maintain a consistent percentage of tail matches across all languages.
An invariant percentage.
Yeah. Specifically, they aimed for 6% of the metadata matches within each language to come from that language's tail concepts, mirroring what OpenAI CLI did for English.
Okay, so find a universal principle, the 6% tail proportion, that they could apply, even with all the linguistic diversity. How did that translate into actually calculating each twang?
It became a two-step process. First, they calculate that global target tail proportion, let's call it P, which is 0.06 or 6%, based on the English data in its known effective threshold, 10.
So establish the target using English as a benchmark.
Exactly. Then, step 2. For each non-English language, they essentially work backwards. They reversely find the language-specific threshold twang that ensures that same proportion, P, the 6% of tail concepts, is represented for that specific language.
Ah, so they adjust T for each language until it hits that 6% tail target for that language's own data distribution.
You got it. This means even languages with smaller data sets still get their unique tail concepts adequately sampled. They aren't drowned out by the more frequent head concepts within that language.
That is genuinely sophisticated. Tailoring the balanced language by language.
And once clang is set for a language, the sampling works like this. Image-text pairs, whose text matches only tail concepts below clang count, are always selected. Pairs matching head concepts above clang are downsampled proportionally based on that clang.
Ensuring representation without overrepresenting the common stuff. Very neat. But pulling this off, processing billions of alt texts, matching against millions of metadata entries across hundreds of languages, you need some serious technical horsepower and efficiency. What were the key implementation choices that made this even computationally feasible?
Yeah, the scale is mind-boggling. Without some serious optimization, it would be impossible. The paper highlights several crucial choices. For the rapid substring matching, which is the core task of finding metadata terms in billions of texts, they adopted the Aho-Karasik algorithm.
Aho-Karasik. Sounds familiar from computer science.
It is. It's a highly efficient string searching algorithm, perfect for matching many patterns against text simultaneously.
Oh.
And they found it was up to 2,000 times faster than the previous brute force substring matching used in the original meta-CLIP.
2,000 times faster. That's
Yeah.
not an optimization, that's an enabler. That makes the whole thing possible.
It absolutely does. A 2000x speed up at that scale is transformative. Another critical choice was lazy metadata loading.
Lazy loading, meaning don't load it until you need it.
Exactly.
Mm-hmm.
Instead of trying to load all the metadata for all 300+ languages into memory at once, which would be completely impossible, memory-wise, they pre-build and store the metadata as an Aho-Karasik automaton for each language separately.
Okay.
Then these precompiled automatons are loaded dynamically on the fly only when the algorithm actually encounters an alt text in a new language during processing. This drastically minimizes memory usage and avoids constant recompilation.
Very efficient. And the third optimization.
The third was clever memory management for probabilities. When you're dealing with concept counts across hundreds of languages to calculate those sampling probabilities, the sheer number of counts can easily overwhelm system memory, leading to out-of-memory errors.
Right, just tracking all those numbers would take huge amounts of RAM.
Yeah. So they used memory-mapped files, or MAP. Think of MAP as a way to treat a file on disk as if it were in memory, without actually loading the whole huge thing into RAM. The operating system handles loading chunks as needed.
Like virtual memory for data files.
Pretty much. This allowed them to handle these enormous counts for sampling without hitting memory limits. These kinds of hardcore engineering optimizations are really the unsung heroes here. They're what make the worldwide curation algorithm practically achievable.
Absolutely crucial. Okay, so they've cracked the data acquisition and curation problem. They can gather and balance data from across the globe, language by language, efficiently. But the paper said even with this brilliant curation, the curse of multilinguality could still persist if the training framework itself wasn't adapted.
That's right. Data is necessary, but not sufficient.
So what was Innovation 3, the worldwide training framework? How did they approach that final critical piece of the puzzle to make it all work together?
This is where they really went beyond just preparing the data. They recognized the training process itself needed fundamental changes to actually capitalize on this amazing worldwide data set and definitively slay that multilingual curse.
Okay.
Their framework introduced 3 key additions. And it's worth noting, they deliberately kept other training settings and the core model architecture, the Vision Transformer, similar to OpenAI or the original Meta CLI. This was important to make sure their findings about these 3 additions were clearly the cause of the improvements and broadly generalizable.
Good scientific practice to isolate the variables. So what was the first addition?
The first one is maybe the most obvious. They swapped the standard English text tokenizer for a multilingual text tokenizer.
Makes sense. Got to be able to read the words.
Exactly. You need a tokenizer that can handle the characters, scripts, and word structures of potentially hundreds of languages. They actually did some relation studies testing different options, comparing various popular multilingual tokenizers.
And what did they find?
The results showed that the XLMV vocabulary yielded the strongest performance, both for English and non-English tasks.
XLMV. Why was that one better?
Largely attributed to its size. It has a massive 900,000 token vocabulary. This huge vocabulary allows it to cover a much wider range of linguistic nuances, characters, and subword units across diverse languages more accurately than smaller multilingual tokenizers.
Bigger vocabulary, better representation. Okay, so the model can now actually read all these languages properly. What was the next critical step in adapting the training framework? You mentioned breaking the curse.
Right. The second addition, and this one is arguably the most critical piece for actually breaking the curse, was scaling scene training pairs.
Scaling scene pairs, meaning showing the model more examples overall.
Yes, precisely. Think about it.
Yeah.
You've just added this massive amount of non-English data. If you kept the total number of image-text pairs the model sees during training the same as an English-only model, what happens?
You'd have to show it less English data to make room for the non-English data.
Exactly. You'd effectively be downsampling English training pairs. You'd be showing the model less English data than its English-only counterparts saw, and that would inevitably harm English performance, basically reintroducing the curse through the back door.
So just adding more diverse data isn't enough if you dilute the signal from the original language by keeping the total training volume fixed. That's counterproductive. What was their solution?
Their solution was quite direct. They scaled the number of scene pairs proportionally to the growth of data size from non-English pairs.
How did they do that technically?
They achieved it by significantly increasing the global training batch size, the number of examples processed in each training step, by a factor of 2.3 times.
2.3x the batch size. Why that number?
That factor likely corresponds to the relative increase in useful data pairs after their worldwide curation compared to the original English-only data set size. The rationale here is really clever.
Go on.
By increasing the total batch size so substantially, they ensured that the absolute amount of English data seen by the model in each epoch, or passed through the data, remains unchanged compared to the English-only baseline. So English performance is protected.
Okay, protects the downside.
But simultaneously, by exposing the model to more overall data in each step, both the original amount of English plus all the new non-English data, they actively encourage cross-lingual learning.
How does that work?
The model starts to implicitly pick up on shared concepts, visual patterns that are described differently across languages, and build more robust generalizable representations because it's seeing this wider variety simultaneously. This mutual exposure, fueled by the larger batch size, is what actively starts to break the curse and create those mutual benefits.
That makes a lot of sense. You're essentially giving the model enough food from all the different language sources in each byte, so no single language's representation gets starved or diluted. Very elegant.
It is.
And the final piece of the training framework puzzle. This one sounds really intriguing. Minimal viable model capacity. What did they discover here? You said this points to a fundamental requirement for truly global AI.
Yeah, this is the part that might really surprise some people. They found that even with all the brilliant data curation, the language-specific thresholds, the multilingual tokenizer, and the scale batch size, even a seemingly large model like the VTL-14 Vision Transformer Large with 14 by 14 patches.
Which was OpenAI's largest CLIP model.
Yeah, exactly. Even that model still suffered from the curse of multilinguality to some extent.
It still showed worse English performance when trained multilingually, even with all the other fixes.
Apparently so. The paper attributes this to deficient capacity. Essentially, the ViT-L model, despite being large, simply wasn't big enough. It didn't have enough parameters or representational power to effectively learn from and integrate the immense complexity and nuance of such a vast, diverse, multilingual dataset.
Wow. It's like trying to fit an ocean's worth of information into a bathtub, even if it's a big bathtub.
That's a great analogy. The model just didn't have the capacity to handle the sheer scale and diversity of the worldwide data properly.
So even with perfect data and clever training, if the model itself isn't big enough, it just can't cope with the global scope. That's a huge revelation.
It really is. And the breakthrough finding here was identifying that the ViT-H14 model, the huge variant, was the inflection point to break the curse.
VT huge.
Yeah.
Significantly larger than ViT large.
Considerably larger. And this model, when trained with their worldwide recipe, demonstrated strong performance improvement in both English and non-English tasks simultaneously. No curse, just gains across the board.
So the model capacity itself was a critical ingredient.
Absolutely critical. It implies that to truly unlock the benefits of scaling data globally, you need a commensurate scaling and model capacity. The data and the model need to grow together, hand in hand.
That raises a really crucial, maybe slightly sobering question about the practicalities of future AI development. What does this imply about the sheer computational resources needed for truly global, high-performing AI? It sounds like training these state-of-the-art global models is going to get increasingly expensive.
It absolutely points towards a significant and likely growing computational footprint. While MetaCelo 2 achieved impressive efficiencies in the curation part, mentioning it takes about 1 hour to substring match and count for all alt-text pairs using 800 jobs, which is fast for that scale.
Right. The data prep seems manageable.
But the full training cost for 29 billion scene pairs using that scaled 2.3x batch size on a massive ViT-H14 model, that would be immense. The paper doesn't spell out the exact petaflop days or GPU years, but it's implied to be a very, very large-scale undertaking.
And that has implications for who can even do this kind of research, right?
Definitely. It's a critical point for accessibility. It suggests that, at least currently, only very large research labs or corporations with substantial compute budgets might be able to train these foundational worldwide models from scratch. It raises real questions about broader participation and democratization at this cutting edge of AI.
A really important technical takeaway with practical consequences. Okay. So, summing up the recipe. Worldwide, language-specific metadata, a clever curation algorithm with language-specific thresholds, and a scaled training framework using a multilingual tokenizer, proportionally increased batch sizes, and a sufficiently large model like ViT-H.
That's the core recipe.
With all those pieces in place, MetaCelo 2 claims to have overcome these long-standing challenges. So now, let's get to the proof, the results. Did it actually work? Okay, this is the moment of truth, right? All that sophisticated engineering, the massive compute. Did MetaCelo 2 actually deliver? Did it break the curse? Did it achieve those mutual benefits? What did the numbers say?
Well, the quantitative results are pretty compelling, undeniably so. When you look at their headline figures, especially for that ViT-H14 model trained with the full worldwide 2.3x scaled data, the results really do speak for themselves.
Okay, lay it on us. How did it do on English performance? Did it avoid the curse?
It didn't just avoid it, it reversed it. The paper states it surpasses its English-only counterpart by 0.8% on ImageNet.
So the version trained on worldwide data was better at the English benchmark than the version trained only on English data.
Exactly. Specifically, the English accuracy on ImageNet went up from 80.5% for the English-only baseline to 81.3% for the worldwide model.
Wow. Okay, that 0.8% might sound small, but breaking through that barrier and actually showing improvement is the crucial point.
It's a profound shift. It's concrete proof that non-English data, when scaled and integrated correctly using their recipe, can actually help English performance rather than being a detriment. Mutual benefit demonstrated.
It's huge. Okay, what about the other side of the coin? How did it do on multilingual tasks? Did it set new benchmarks there?
It absolutely did. MetaCelo 2 established new state-of-the-art results across several key multilingual benchmarks. For instance, on CVQA.
That's the multilingual visual question answering one.
Right. It achieved 57.4% accuracy. The previous state-of-the-art was 49.8%. That's a massive jump, nearly 8 absolute percentage points.
A huge gain. What else?
On Babel ImageNet, which tests image classification across many different languages, it hit 50.2%, whereas the previous best was 46.4%. Another solid improvement.
Okay.
And for XM3600, which is a multilingual image-to-text retrieval task, finding the right text description for an image across languages, it reached 64.3%, beating the previous state-of-the-art of 62.8%.
So consistent, significant improvements across a range of different multilingual challenges. These aren't just marginal gains.
No, there's substantial steps forward, demonstrating broad multilingual capability.
Now, what about efficiency? You mentioned the huge compute for training ViT-H, but did they get these gains by just throwing vastly more data at it during training or using super high-res images?
This is another really fascinating part. They actually achieved this new state-of-the-art performance while using fewer scene training pairs overall compared to some other leading models.
Fewer pairs. How much fewer?
Specifically, the paper mentions using only 72% of the scene pairs compared to the SIGLIP series of models, which were previous strong contenders.
Wow, so getting better results with significantly less training exposure.
Yeah. And they also did it using a lower resolution for the images during training 224 by 224 pixels compared to, say, MSIGLIP, which used 256 by 256 pixels.
So better results, fewer training examples seen, lower resolution images. That points to a really significant leap in efficiency, doesn't it?
It absolutely does. It means they're getting more bang for their buck, extracting more learning signal from each data point in each pixel. This has really positive implications for maybe slightly reducing training costs down the line, potentially faster inference, and just better overall resource utilization.
Okay. The numbers are definitely impressive. Clear wins on English, new soda on multilingual, and surprisingly efficient in terms of data and resolution. But let's look beyond the benchmarks. What are the more desirable, maybe qualitative, results of this approach? What does this mean practically for the future of AI models?
This is where the implications really start to broaden out. I think one of the most significant takeaways conceptually is the clear demonstration of mutual benefits.
The win-win scenario.
Exactly. Non-English data isn't just handled, it actively supports and improves the English models, and presumably vice versa, across languages within the model. And as the paper rightly points out, this capability is becoming critical in the era when English data is depleting.
That's a really interesting point. Are we actually running out of useful English text and image data on the web?
There's a growing consensus that we're approaching saturation, especially for high-quality, unique English data. So being able to effectively tap into the vast reserves of non-English data isn't just about fairness or global reach anymore. It's becoming a strategic necessity for continued AI progress. We need new sources of information and diverse perspectives to find novel patterns and keep improving these models.
So leveraging global linguistic diversity isn't just nice, it's essential fuel for future AI growth. That's a powerful argument.
It really is. Secondly, MetaSylab 2 offers truly full multilingual support in a properly integrated way. The model never drops image-text pairs simply by languages. It uses all the curated data from the start. This is different from some previous systems that might have filtered or simplified non-English content, and it contributes to its strong performance.
Using everything it's given.
Right. Thirdly, and this is crucial, it achieves native language supervision. The models are learning directly from alt texts written by native speakers in hundreds of languages, not from potentially flawed synthetic machine translations.
Avoiding the translation trap.
Exactly. This avoids the biases and the often lost nuances that machine translation introduces. It means the model captures a much more authentic richness of human language and how people naturally describe the visual world.
That feels like a huge win for the accuracy and the richness of the model's understanding. What about the impact on how these models see the world, particularly culturally?
This is another key benefit. Because it trains on truly worldwide data, MetaSylab 2 inherently fosters cultural diversity in its understanding. The paper says it retains the entire global distribution of images, inheriting comprehensive cultural and socioeconomic coverage.
And that's not just a sort of nice-to-have feature. It has technical benefits.
Oh, absolutely. It has direct, tangible technical impacts. The paper notes it improves geolocalization and region-specific recognition. Why? Because the model has been exposed to a vastly wider array of visual contexts, objects, clothing styles, landscapes, activities, things that vary hugely around the world.
So it's better at recognizing, say, a specific type of regional food or architecture because it's actually seen examples linked to native descriptions.
Precisely. This makes the model fundamentally more robust and effective for real-world global applications, where a simple concept like cup or house can look incredibly different depending on the cultural or geographical context.
That makes sense. And I remember reading something about their no-filter philosophy. What does that mean, and how does it help with this diversity aspect?
Ah, yes. The sophisticated curation algorithm they developed, particularly the language-specific thresholds applying, allowed them to remove what they called the last filter. In previous systems, there might have been an implicit or explicit check. Is this alt text in English? If not, maybe handle it differently or drop it.
The English gatekeeper.
Kind of. By removing that necessity through their language-aware curation, MetaCLI 2 minimizes biases introduced by filters themselves. When you remove that English-centric conceptual filter right at the data curation stage, you naturally open the door to a much broader, more representative data set of the world's visual and linguistic information. More diversity flows in.
Letting the world's data speak for itself more directly.
In a sense, yes. And finally, thinking even broader. What are the impacts of this work on foundational data itself, beyond just CLIP models? Well, this effort provides a truly foundational data set of image-text pairs at worldwide scale, curated with a transparent, principled method. This data set itself is immensely valuable.
For training other kinds of models.
Exactly. It's not just for CLIP. It can benefit other critical AI efforts that rely on high-quality multimodal data. Think about training the next generation of multimodal large language models like maybe Llama 3 or future versions. Think about improving self-supervised learning models for vision, like WebDino, or even enhancing cutting-edge image generation models like DLE or Stable Diffusion variants.
Because they all need good, diverse image-text data to learn from.
Precisely. This curated, worldwide data set, because it's open-sourced along with the methodology, can potentially accelerate innovation across the entire AI landscape by giving all these different types of models a truly global starting point, a richer view of the world.
Okay. And one last technical point they mentioned was embedding quality. It might sound a bit technical, but what does it really signify when they say MetaCLI 2 shows good scores in both alignment and uniformity? Why does that matter?
That's a great question to unpack. When we talk about embedding quality, we're essentially judging how well the model has organized its internal map of concepts, how it represents images and text numerically.
Okay.
Alignment means that the representations for images and their correct text descriptions are close together in that map, in that high-dimensional embedding space. They align well. So the embedding for a picture of a cat is near the embedding for the word cat, and hopefully far from the embedding for car.
Makes sense matching pairs are close. What about uniformity?
Uniformity means that the embeddings for all the different images or texts are spread out reasonably well within that space. They don't all just clump together in one corner. Good uniformity suggests the model is using the whole representational space effectively to distinguish between many different concepts.
So alignment means related things are close. Uniformity means unrelated things are spread out.
That's a good way to put it. Getting good scores in both alignment and uniformity on data the model hasn't seen before, holdout data, indicates that the model has learned high-quality, relevant, and well-distributed representations. It suggests its internal understanding of the world is robust, well-organized, and likely to be broadly useful for many downstream tasks that rely on these embeddings.
So in essence, MetaCLI 2 isn't just adding more languages. It's fundamentally improving the model's deep understanding of the world by truly leveraging its full diversity, and the embedding quality reflects that deeper, more organized understanding.
That's a perfect summary. It's a significant leap forward, not just in breadth, but in depth of understanding.
Okay, this has been fascinating. We've covered the groundbreaking innovations, the really impressive results. It feels like a major step. But, no research paper, no matter how good, answers absolutely every question.
Never does. Science is incremental.
Exactly. So what does this MetaCLI 2 paper not fully unpack? Where are the lingering questions or areas where we might want to look next for deeper technical insights or future research directions?
That's always an important lens to apply, what's not said. One thing is, while MetaCLI 2 clearly demonstrates that English and non-English data help each other, the mutual benefit is there in the results. The paper doesn't fully delve into the precise mechanisms of that mutual benefit.
Meaning how exactly it works under the hood.
Right. How exactly do different languages teach each other within the model's internal representations? Is it mainly about reinforcing shared visual concepts? Because, say, a dog is described in hundreds of languages, strengthening the core dog concept.
Or is it something deeper?
Or could it be that different languages offer unique linguistic structures, different ways of carving up the world or describing relationships that somehow enhance the model's general understanding of semantics or compositionality, even in ways that benefit English tasks? We see that it works, but the why at that granular representational level isn't fully explored.
That's a really interesting question for deeper research, understanding the cross-lingual transfer at that fundamental level. What else from a technical standpoint felt maybe less explored or left open?
Well, another crucial aspect, especially when you think about replicating or building on this work, is the absolute computational footprint of worldwide scaling.
We touched on this, the ViT-H requirement.
Exactly. While the paper rightly highlights the impressive efficiency gains they made in the data curation step, that 1 hour on 800 jobs is remarkable. The full training cost for churning through 29 billion scene pairs with that scaled-up batch size on a monster like ViT-H14, it's clearly immense.
And the paper doesn't give the exact number.
It doesn't provide a comprehensive breakdown of the total petaflop days or the energy consumption or the wall clock time needed for that full training run. It's implied to be huge, but the specifics aren't there.
And that lack of detail makes it hard to assess the true cost and, again, the accessibility.
Precisely. It leaves open questions about the exact resources required and reinforces the concern that, for now, this kind of from-scratch worldwide training might remain primarily the domain of organizations with very significant computational resources. How can this scale of training become more accessible? That's a big question.
A very practical, important concern. Anything else about their specific methodology that might warrant more investigation, maybe around the curation?
Well, one could potentially explore the nuances of the language-specific thresholds to lang. Their approach hinges on that invariance assumption, maintaining a consistent 6% tail proportion across all languages based on the English benchmark.
Right, the 6% rule.
The question is, how sensitive is the final model performance to that specific 6% figure? Is it truly the optimal percentage for every language family or data distribution? Could some languages, perhaps those with very different conceptual frequency patterns or maybe less web data overall, actually benefit from a slightly different tail proportion, maybe 5%, maybe 7%?
And how would you even figure that out?
That's the challenge. How would you programmatically discover and optimize for these potentially language-specific optimal percentages? It points to a possible area for further fine-tuning and perhaps squeezing out even more performance by adapting the curation algorithm further based on deeper linguistic or statistical properties of each language's data.
Interesting. So optimizing the optimizer, essentially. Those are all great points for future technical research within the scope of the paper's approach. But looking beyond the paper itself, what about the broader ecosystem? What are the ongoing challenges for even evaluating models like MetaCLI P2 in a truly global way? How do we know how well a global model is really doing if our measuring sticks are still kind of local?
You've hit on a really critical, persistent challenge for the whole field, this state of multilingual benchmarks. And the paper itself is refreshingly candid about this, acknowledging the limitations on benchmark quality.
What's the core problem with the benchmarks?
The core problem is that most of our existing high-quality, carefully curated evaluation data sets, things like the Venerable ImageNet, CoCoCo, and others that we rely on heavily, were developed primarily based on content scraped from North America and Western Europe, NA plus EU, and focus overwhelmingly on English.
So our best tests are geographically and linguistically biased.
Deeply so, often reflecting a Western English-centric view of the world and the concepts deemed important. This creates a significant mismatch. We now have models like MetaCLI 2 that can learn effectively from truly worldwide data, but our ability to comprehensively and impartially measure their effectiveness across all those diverse global contexts, it's still lagging behind.
It really is like we've built this amazing multi-tool designed for the entire planet, but we're mostly testing it with screwdrivers and wrenches from just 1 or 2 continents.
That's a perfect analogy. And building truly unbiased, comprehensive worldwide benchmarks is incredibly difficult. It's not just about translating existing concepts. It requires grappling with the immense complexity of covering diverse concepts across geolocations, cultures, and languages. What's a common object in one place might be unknown in another. How do you even define a fair set of global concepts?
A huge challenge. Are existing multilingual benchmarks not good enough?
They're useful starting points, but they often have their own limitations. For example, the paper mentions XM3600, which aims for multilingual retrieval. But it might inherit biases towards Western imagery because it relies heavily on the OpenImages dataset, which itself has known geographical biases.
Okay.
Another example is GOD, which tries to crowdsource geographically diverse images. But crowdsourcing brings its own challenges, like potential quality issues in the collected data or annotations, and possible demographic bias among the crowd workers themselves who might not represent a truly global population.
It sounds incredibly hard to get right. Ensuring quality, diversity, and lack of bias all at once on a global scale.
It is incredibly hard. Efforts like CVQA try to use experts to ensure quality, which is great, But the paper notes it's still a long and resource-intensive endeavor. Building these truly general, high-quality, culturally diverse benchmarks requires deep cultural and linguistic expertise, careful sampling strategies, and significant investment. It's an ongoing arms race, really. Model capabilities are advancing rapidly, especially with breakthroughs like MetaCLIP2, but our evaluation tools are struggling to keep pace.
So what's the takeaway there for the future? If MetaCLIP2 shows we can build models that leverage worldwide data effectively, but our ability to measure that effectiveness comprehensively is still catching up, what's the path forward for the field?
It means the focus needs to be twofold. Yes, continue pushing the boundaries on model architecture, data curation, and training techniques, building on insights like those from MetaCLIP2. But equally importantly, the field needs a massive, concerted investment in developing the next generation of robust, truly globally representative evaluation methodologies and benchmarks.
We need better measuring tapes for our better models.
Exactly. Without them, we can't fully understand the capabilities, the remaining limitations, or the potential biases of these increasingly powerful worldwide AI systems. It's definitely an exciting space, but one with significant evaluation challenges still ahead.
This has been an absolutely incredible deep dive, really getting into the nuts and bolts of MetaCLI2 and what it signifies.
It really is a landmark paper, I think, a testament to how focusing on the fundamentals, meticulous data engineering, strategic scaling of compute and model capacity, and prioritizing native data can lead to breakthroughs. It moves the needle on truly global AI.
So let's try and wrap this up for you, our listener. What's the big idea to take away from all this? It seems the core insight is that this curse of multilinguality, which plagued models like CLIP for years, it wasn't some inherent, unavoidable law of AI physics.
Not at all.
Instead, it looks like it was more a symptom of insufficient scaling. Specifically, not enough scale and sophistication in the metadata, in the curation algorithms, and crucially, in the model capacity itself.
Right. Those three pillars needed to be scaled up together.
And when those factors are carefully designed and scaled jointly, as MetaCLIP2 definitively showed, something amazing happens. English and non-English data stop fighting each other. They actually become mutually beneficial.
It's not a zero-sum game anymore. It becomes a positive-sum, synergistic relationship where learning from Spanish helps English, learning from Japanese helps Swahili, and everything helps everything else build a more robust understanding.
This work really does move us closer to that vision of genuinely global AI models, doesn't it? Models that can learn directly from the staggering diversity of the world's linguistic and visual information, not just the fraction represented on the English-speaking internet.
Absolutely. Learning from the rich tapestry of human experience across all cultures and languages, and the fact that Meta has open-sourced the comprehensive worldwide metadata they built, along with the code for their curation algorithm. That's huge.
A big contribution to the community.
It's a powerful invitation, really.
Yeah.
An invitation for the entire research community to embrace this worldwide multimodal web and to build upon this foundational recipe.
Absolutely. Which leads us to that final provocative thought to leave you with. If the future of AI models is truly global, if we can effectively leverage the richness of all human-generated data, every language, every cultural viewpoint captured in images and text, every visual nuance from every corner of the globe, what completely new capabilities or maybe even entirely new forms of machine intelligence might emerge? Things we can't even conceive of right now, stuck as we've mostly been within a largely English-centric framework.
It's a profound question. What happens when AI truly starts to learn from the totality of human expression? A very exciting prospect for the field indeed.
Definitely something to think about. And if you want to stay updated on the latest AI and ML research papers like this one, remember to visit our webpage. The link is in the bio. Thank you so much for joining us on this deep dive today.
Yeah, thanks for tuning in.
We'll see you next time.